Hey guys! Okay, so we are out of my little office slash guest bedroom, and we are not on campus. So we are in my living room now, and I'm gonna hope that the dogs stay quiet. I'm gonna hope that the service is fine, and we are just gonna get through chapter 13 today. Koopy, it's not time for that, Bubba. You can go meet people, but it's not time to play with that. Well, here's one of them. That's Cooper. Say hi, Bubba. What are you doing? We have 3 border collies because we're crazy people. So guys, last time we were talking all about chapter 12. Thank you so much. Today we're going to be talking about chapter 13, which is evidence of evolution. So I'm going to go ahead and share my screen with the PowerPoint, which is available to you on Blackboard already. Koopy, I got a lecture, Bubba. Okay, get down. I love you. All right, so chapter 13 is evidence of evolution. I'm going to try to make this short. It's a pretty short chapter compared to chapter 12. So let's go. All right. We have evidence that life on Earth arose 3.8 billion years ago. 3.8 billion years ago, that's about right here. Okay, actually, wait, why is my arrow over there when it literally says 3.8 right here? Anyway, 3.8 is where it says 3.8. And we know that the origin of Earth was somewhere around 4.6 billion years ago. Okay, so things have been happening for billions and billions of years, and throughout this time, humans have been here for like a second, a nanosecond, that's not a thing, but a nanosecond in actual time, in historical time. So changes in body structures and molecules have slowly accumulated throughout this time, producing the variety of organisms that we see today. Now, this geologic time scale is much more intricate than just a little time scale like this. Okay, so we divide history of Earth into eons and eras, and typically you have an eon that is subdivided into multiple eras. Okay, periods are defined at Eden, stop. Guys, forgive me. It's actually really early in the morning. So periods are defined by major geological or biological events like mass extinctions, okay, which we're actually going through a mass extinction event right now. All right, so if we take a look at some of our eons, some eons, okay, like right here, are subdivided into different eras. Others, like these, the Hadean era, eon, are not divided into specific eras, okay? But you can see tons of amazing things happen here. So you have the eon where the Earth forms, you got the eon where life starts, and then all of a sudden, 90 to 500, you have this explosion of life. Okay, and the explosion of life, this is talking about the ancestors of every living thing today came about in what we call the Cambrian explosion. Okay, so you can see all, in fact, I encourage you to look at this PowerPoint slide and just see how amazing, how just the timeline of all of these things happening, okay? Small prokaryotes coming around in the Cambrian explosion, but you also have like bony fishes, and then you have the first dinosaurs, and then you have the first birds and mammals, pollinating insects diversify. You got a ton of stuff going on in the hundreds of millions of years since that Cambrian explosion. All right, paleontology. The study of fossil, either relative dating or radiometric dating around when this organism died, okay? And we'll talk all about that today. So fossils provided the original evidence for evolution. It said, hey, okay, even if we have something similar to this today, it actually looks pretty different. we have fossils of like, not only things like leaves, not only things like bones and stuff like that, whole organism wise, but we also have fossils of like pollen grains. Okay, so it's like these amazingly well preserved, not even organisms, but molecules that we use to study current day life. Okay. All right, so the fossil record is incomplete, meaning that we know that a fossil that we had looked very similar to something that's living today, but we don't have that sort of bridge, that organism that is like perfectly between the two. We don't normally get to have that, and that's because the fossil record is incomplete. And that's because some organisms will not fossilize. Say like if you have like slugs or something like that, slugs with soft bodies, anything really with a soft body without bones or without an exoskeleton or something like that, they're mostly going to fail to fossilize. And that's the same thing with us, right? What is the parts of our bodies that can be crystallized in the earth, that we can literally find in fossils? Are you finding your skin? No. Are you finding your hair? No. So your bones, okay, are what are going to be preserved in the fossil record. So another reason why the fossil record is incomplete is because of erosion. Erosion happens, movement of Earth's plates sometimes will destroy fossils, okay, fossil evidence. So here in this picture, you have organisms that were known as ammonites, and these are extinct organisms, okay? Extinct organisms not living today. We have ancestors, well, okay, so they are the ancestors of organisms that are living today, but what's amazing is that these organisms, these marine organisms, were found in landlocked Oklahoma. Okay, if you find a marine organism in landlocked states, what does that tell you? Well, it tells you that once, probably millions of years ago, water once covered that area. Okay, so we have a ton of evidence like this that Earth's crust has shifted a lot. So you have this simpler sort of dating of fossils, which says that newer rock layers have newer fossils, more recent fossils. Older, deeper rock layers have older fossils. Okay, so that's called relative dating. Now, you assume lower rock layers have older fossils than newer layers, but very important, relative dating, it's just relative to how deeply you basically found the fossil. It does not assign a specific age to that fossil. And here is absolute dating. Now, a type of absolute dating, which we'll get into with all of this down here in a second, but basically absolute dating, it uses chemistry, different isotopes of different elements in order to determine how long ago a fossil formed. So the reason that we can do absolute dating with different isotopes is because every living organism is carbon-based. Every living organism, regardless of whether you're a sea anemone or a human, doesn't matter if you're a banana or a human, it doesn't matter, okay? You are made up of the same things, okay? Literally the same stuff makes you up. So we're able to determine how much of specific isotopes are left in the remnants, in the fossil remnants, and then that allows us to date these fossils. So a type of absolute dating is called radiometric dating. Radiometric dating, which I think I called radioactive dating earlier. Radiometric dating uses radioactive isotopes, okay? And basically the way that this happens is that as we're living, we have a ton of the isotope carbon-12. This is a stable isotope of carbon that makes up our whole bodies, okay? We're carbon-based organisms. And as we're just going about living our lives, sometimes, in fact, all the time, okay, we will incorporate another isotope of carbon, carbon-14, which is a radioactive isotope. Just from living, we incorporate that into our body, whether we're breathing something in or whether we're eating something or drinking something, we're incorporating these radioactive isotopes. It is a very, very small percentage of our bodies that are made up of these radioactive isotopes. But what's super interesting is that while you're alive, replacement equals decay. So the amount of this radioactive isotope that comes into our bodies is equal to the amount that leaves our bodies, okay? Now, once you die, are you replacing that radioactive isotope anymore? No, you're not. Are you accommodating any more radioactive isotope? No. So you only have that decay. So we're able to use the decay and how much radioactive isotopes are left in an organism, in the remnants and the fossil remnants, to determine how long that fossil has been there. All right, so throughout life, organisms accumulate carbon-14. That's a radioactive isotope. An isotope is basically just a different version of a carbon atom, for instance, okay? So they're both still carbon. They're just slightly different at the subatomic level, okay? This is not a chemistry class. We are not going into protons, neutrons, electrons, everything like that. So don't worry about that. But you, as a human, as an organism, you're incorporating C12 and C14, okay? I said that it's a super, super low ratio. One radioactive carbon-14 isotope to 1 trillion carbon-12 isotopes in your body. So for every 1 trillion carbon-12 isotopes, carbon-12 atoms, you have one of this radioactive kind, okay? So 1 trillion stable carbon-12 to 1 radioactive unstable carbon-14 isotopes. Living organisms, when they are alive, replacement equals decay. And decay is interesting for carbon-14. You incorporate it as this radioactive isotope, and then as it decays, it is going to leave as nitrogen-14. It's going to leave as an isotope of nitrogen, okay? As it decays, it just becomes something different. And so as it's leaving, but okay, so we can measure how much is left, but it's only really relevant after you have died, okay, right? Because once you have died, you're not having this sort of replacement anymore, and that's when we can tell actually how long that fossil has been around. So after the organism dies, no more carbon-12 or carbon-14 is added. So instead of having this incorporation, you just have this carbon-14 leaving as nitrogen. It decays at a constant rate, leaving the organism as nitrogen, and now you have this half-life. So if we know the radioactive isotopes within an organism and within a fossil, then we know the half-life. We can test the half-life, okay? Meaning that, so for instance, the half-life of carbon-14 is 5,730 years. So every 5,730 years, the amount of carbon-14 is reduced by half, okay? And then half, and then half, and then half. But as you can see, it would take a long time. So we're able to say within that length of time, hey, this fossil has probably been there for 2,000 years versus this fossil has been here for over 10,000 years, okay? All right, so by determining the amount of carbon-14 in a fossil, scientists can estimate when that organism lived. Now, the half-life of carbon-14, we said that it's 5,730 years. This is relatively low, so we can use it for more recent sort of fossils, anything where death occurred up to 40,000 years ago, okay? We have other isotopes that we can use to date fossils much further away, okay, that are much older. So for instance, potassium-40 is used for dating rocks that are older than 300,000 years old, and there are others that are even further out, okay? But so this type of dating, this type of absolute dating, we're using half-life, the half-life of these radioactive isotopes to figure out how old that fossil is. All right, which rock layer, A, B, or C, should have fossils with the most carbon-14? Which rock layer, A, B, or C, should have fossils with the most carbon-14? Now, let's talk about this. Is this talking about relative dating? Or is this talking about absolute dating? Are you figuring out a date, a number of years ago that this organism died? No, so you're talking about relative dating. What does relative dating tell you? It tells you that newer fossils died more recently, organisms that died more recently are on the top layers, and older fossils are on these bottom layers. So if you have the most carbon-14, that's the radioactive carbon isotope that we incorporate into our bodies when we're living, and it leaves as nitrogen. So if you have an older fossil, you'll have less carbon-14 because it has started decaying. If you are a newer fossil, you will have more carbon-14. Get comfy. What? Hold on. Why? Why did you do that? Jesus. All right, hold on. Got my whole setup over here. Like, you got a whole house. Just go lay down. Jiminy Christmas. All right. Newer fossils on top, older fossils on the bottom. So you would expect the rock layer with the most carbon-14 to be the newest rock layer. Okay, so that's A. Now we're going to practice a half-life question. Okay, so here we have phosphorus-239. Oh, actually, plutonium-239. So sorry. What am I even doing? All right, plutonium-239. The half-life of plutonium-239 is 25,000 years long, okay? So every 25,000 years, the amount of plutonium-239 is cut in half. If 16 grams of plutonium-239 are initially present, so as soon as this organism was alive and then dies, it has 16 grams of plutonium-239. How many grams are present after 25,000 years, after 50,000 years, and after 75,000 years? So I'm gonna stop sharing for a second. I want you to, you can pause. In fact, you should pause, try that question for yourself and see if you understand half-life. But I have, well, and we're gonna see, because this is not as great as in my office where I've got my whole setup, but I have written this out already for us, okay? Because I knew that this was gonna be awkward. So we've got, wow, Eden, we have plutonium-239 with a half-life of 25,000 years. Starting, our initial amount of plutonium-239 is 16 grams. So when we're at 0 years, we have 16 grams of plutonium-239. Then, if the half-life is 25,000 years, if you go from 0 to 25,000, what you're gonna do is you're gonna take 16 grams, multiply it by half, or just divide it by 2. That's literally what you're doing. Take 16 grams, divide it by 2. Now you've got 8 grams. You would have 8 grams of plutonium-239 at 25,000 years. Another 25,000 years, because that's our half-life, and that's what the question asked for, you would start with, from 25,000, starting with 8 grams. To get to 50,000 grams, you have to divide by 2 again. That's 4 grams. 50,000 to 75,000, you start with 4 grams from here, divide it by 2, and now you've got 2 grams, okay? So after 75,000 years that this that this organism has been dead, that we have a fossil, you went from 16 grams of plutonium-239 to only 2 grams of plutonium-239. 75,000 years, and you still have plenty. You would have another 50,000 years before it even gets we're still able to measure it, okay? reliably, because once it gets like too low, you're going to want to find a different isotope to date these fossils with. Okay. All right. So, okay. I'm going to share my screen again for a second because we have another question. All right, researchers used a radioactive isotope with a 25,000 year half-life to date a fossil to 100,000 years ago, meaning that this organism died 100,000 years ago. And this radioactive isotope, doesn't matter what it is, because we know the half-life, which is 25,000 years. This fossil contains what amount, as much of the isotope as does a living organism. So it's going to be a fraction of the amount that a living organism has, okay? Now, I'm going to take you through this. If we have, I'm going to stop sharing again. So if we have any isotope that has a, I'm trying to like figure out how I'm going to actually do this. Any isotope that has a half-life of 25,000 years. Well, to get to 25,000 years, to cut it in half, remember, you had to start with 0. So you're going 0 to 25,000, okay? And then you're doing another half-life, getting it to 50,000, and then another half-life from 50,000, another 25,000 to 75,000, and again to get us to 100,000. Now this is important because every time you have this arrow, every time we're going another 25,000, another 25,000, another 25,000, we are reducing it by half. Okay, so we are reducing it by half 4 times. Now, if you don't know how to multiply fractions, you should. It's an excellent skill to have, okay? I hope that y'all can see this, but I just want you to take those 4 1/2s and line them up like that, okay? The way you multiply fractions is you multiply your numerators and you multiply your denominators, okay? So your numerators are all 1, so you don't have to really do anything with them. It's gonna be 1 over whatever. So 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Okay, so at 100,000, at a 100,000 year fossil with some isotope that has a half-life of 25,000 years, by 100,000 years, this organism has 1/16 the amount of that isotope that it had when it died, okay? That's how you do that. If you are confused, if you didn't get that, just pause, go back, figure it out, email me, like do whatever you need to do, okay? And guys, that was it for this part. I'm gonna record another one for the second part of chapter 13, but that was it for right here. So I'm going to log off and I'll see you in a second. Bye.